In today's lesson, I'm going to walk you through a typical entropy question found in A-level chemistry, advanced placement chemistry, and International Baccalaureate. But before we look at today's question, I'm going to recap the formulas that we will be using. So it's the formula for enthalpy, entropy, and then the free energy, the Gibbs energy. So the enthalpy change for reaction delta HR is equal to the enthalpy of the products minus enthalpy of the reactant. So H, by the way, is the symbol for enthalpy. So it's just the difference in energy between the products and reactants, and the units for enthalpy are always the same as kilojoules per mole. Then for entropy, so delta S, system, is the entropy of the products minus the entropy of the reactants. So again, it's just the difference in products and reactants, and the units for entropy, which you have to be careful with, are actually in joules per mole per Kelvin. Okay, so Kelvin is the measurement of temperature. So 273.15 Kelvin is equal to 0 degrees C. So that means any temperature you are given in degrees C, you must turn into Kelvin. Finally, then, the equation that brings together the enthalpy, the entropy, and the temperature for reaction in one formula is the Gibbs energy. So it's delta G is equal to delta H minus T delta S, where delta H is the enthalpy, delta S is the entropy, and T is the temperature. Okay, so one important thing I will say is the Gibbs energy is usually expressed like enthalpy in kilojoules per mole. So you've got to remember to make sure the units are all the same. So what I do is I turn the entropy from joules into kilojoules by dividing by 1,000 and then making sure that the temperature is in Kelvin as explained above. So we have a displacement reaction, as I said. So a displacement reaction is where a more reactive or more oxidizing species displaces a less reactive species. And if I just zoom out, we can see we've got three things to calculate: delta H, delta S, and delta G. So that's exactly what I'm going to do. So delta H for the reaction is going to be the products. So if we look at the products, we have carbon monoxide, and we can see there's three lots of it. So it'll be 3 times minus 111. Aluminium is a product as well, but you will notice that hasn't got an enthalpy of formation. It's 0. The reason why is because it's an element, and elements are not chemically formed like compounds. So that's 0 minus the reactants, and we can see we have aluminium oxide, one lot, so minus 1669. And again, carbon is 0, so we don't need to include that. So we've got minus 333 plus a minus and a minus makes a plus 1669. So let's work that out. And that gives, so that's the enthalpy change. Right, just a note, you can see that that number is positive. So that tells me that it's endothermic. Right, same drill now for the entropy. Delta S is equal to the entropy of the products. So it's going to be 198. The 3 times 198 for the carbon monoxide, plus the aluminium, which has an entropy of 28, so 2 times 28, minus the entropy of the reactants, which will be aluminium oxide, which is 51, plus 3 lots of carbon, which has an entropy of 6, so 3 times 6 is 18, so we've got something that looks like that. So that comes to 581 joules per mole per Kelvin. Now, remember what I said previously, watch out for units, okay? Just going to underline that in a different color. That's in kilojoules, that's in joules, because we will need to convert later on. Right, finally, the delta G equation. So delta G equals delta H minus T delta S. So delta G equals delta H, which is 1336, minus, always put the T delta S part in brackets, right? So the temperature which this has been performed at, or we're testing, is 298 K. So it says, suggest why this reaction is not feasible. So just before we work this out, for a reaction to be feasible, delta G has to be a negative value. And for it to be not feasible now this is important, at the stated temperature. Just because it's not feasible when you've calculated, it doesn't mean it's not feasible full stop. It just means at the stated temperature. So that's really important. And the stated temperature in this case is 298 K, then delta G will be a positive value. If this reaction is not feasible at 298 K, we're expecting a positive value for delta G. If it is negative, then it will be feasible. So remember, feasibility is temperature dependent. Just because a reaction doesn't work at one temperature doesn't mean that it won't be feasible at another. So we put in 298 K and we times in this by the entropy. Now I'm going to turn the 581 into kilojoules. So I'm going to divide it by 1,000. So watch out for that. So it's 0.581. So I've divided that by 1,000. Just a reminder there. It's just now all in the same unit. So this simplifies to 1336. So 298 times 0.581. Just doing it bit by bit so you can see what's going on. Minus 173.138. And then the final answer is, put it down here, 1162.7 kilojoules per mole. So we can see that this is a positive value, and because it's positive, it's therefore not feasible at 298 K, which is 25 degrees C. Calculate the temperature above which this reaction is feasible. So for it to be feasible, delta G has to be equal to 0 or negative. So delta G must equal to be 0 or negative for a reaction to be feasible. So if you think of it like the smallest possible value delta G can be for it to be feasible is 0. So let's put that in. So delta G equals delta H minus T delta S. So 0 equals delta H minus T delta S. I'm going to rearrange this equation because we're asking for a temperature. So T delta S is equal to delta H. Therefore, finally, the temperature for which this is going to be feasible will be found by doing T equals delta H over delta S. Now, do I have this information? Yes, I do, because I just worked out the enthalpy to be 1336 and the entropy to be 0.581 in kilojoules. So I can already see this is going to be a huge number. 1336 divided by 0.581 gives me, so let's give that value some context, right? So if I just turn, it doesn't ask for this, but if we turn into degree C, because often we're so used to working in degree C and Fahrenheit, it's easier to see a temperature in degree C. So to turn that into degree C, I just take away 273.15, and then that gives of around 2226.3 degrees C. So before this reaction becomes feasible, which is the displacement aluminium out of its ore by carbon to produce aluminium, the temperature has to be at least 2026 degrees C, which is an enormous number. Now, let's just say the reaction gets to that temperature, and that temperature is provided, so then on paper it will be feasible. But that doesn't tell us anything about the rate, so it may actually begin to work at 2026 degrees C, but it may be really, really slow. So the rate of reaction for the displacement of that aluminium by the carbon might be so slow that actually 2026 is not enough. You need an even higher temperature again. So maybe going up by another 1000 degrees C for it to become feasible, which then can be used to explain, if you think back to the reactivity series, why carbon is not used to displace aluminium. Instead, we use electrolysis, probably because of the reasons we just found out, that it would take thousands of degrees C just to get this to work, which would be too expensive and probably too dangerous. Right, I hope that was helpful. If you've got any questions about that process, the walkthrough, the equations, anything, please ask down below and I will get back to you as soon as I can. If not, I look forward to seeing you in the next one.